This is a short tutorial about the Church-Yoneda identities. The Church-Yoneda identities are not well known, and I would like to talk just a little bit about what they are and how they are used. The Yoneda identities are known in category theory under the name the Yoneda lemma. The church encoding is known in category theory under completely different names, and it's working in a very different way. The related category theory result is the so-called Lambeck theorem, which is about initial algebras and the functors. And it says that the initial algebra is one where the algebra map is an isomorphism. But this actually does not help very much for the programming side of these identities to understand how they work and how to use them. So in this tutorial, I will not be talking about category theory at all. And instead, I will be talking about just a programmer's view of these identities. So the church encoding is the subject of my tutorial that I recorded previously. And it is that the fixed point of the functor f can be expressed as this type. So it is the least fixed point of the functor f. The Church-Yoneda identity is an encoding that looks like this. So it is different from the church encoding in that here, instead of r, I have g of r, where g is some other functor. And it turns out that this type encodes g of the fixed point of f. So the functor g applied to the fixed point of f, which was encoded like this. And this works where f and g are arbitrary covariant functors. Now, the important assumption that needs to be made is that all functions here are fully parametrically polymorphic, which means that this quantifier for all r means the code of this function. So when we implement the value of this type, then there will be a function of this type with a type parameter r. This function, the code of this function, may not examine the actual type r that is passed to it at runtime. The code must work with values of type r without knowing what that type is. That means it must work in the same way for all types that are passed to it under r. And if this is so, then one can prove that this function will satisfy what is called the strong dinaturality law. And this is a generalization of the naturality law for functions that are not of the form of natural transformations, because this is not covariant in R. This is covariant in R. This by itself is covariant in R, but this whole function is not of the form something of R that is covariant being mapped to something else that is covariant. So naturality cannot be applied to this function. It is not a natural transformation. But it turns out that another more complicated law applies to it, and that law is called the strong dinaturality law. I wrote down what that law is, but it will not be very illuminating right now if I go into that detail. But essentially, you can think about it as a natural generalization of what naturality law must be. So if we are only looking at functions of this type that satisfy the strong dinaturality law, then one can prove that the set of all functions of that type is one-to-one isomorphic to the set of all values of this type, which is the functor g applied to the least fixed point of f. Now this seems to be a very abstract statement, and it is because it works for all f and g. Another thing I would like to mention immediately is that it is far from obvious that this is true. It is also far from obvious that this is true, that the least fixed point type, the least fixed point of a functor f is the type given by this type expression. It is far from obvious that this is correct. It is not easy to prove. I prove it in my book, and it takes some pages of calculation and derivation. There are very few tutorials online that explain how that works. There's one unpublished paper by Wadler, which is a tutorial showing how these encodings work. It does give a more or less detailed sketch of the proof, but it still does not go through all the necessary details, which would be necessary for someone who is not very familiar with this entire topic to understand the proof. From the programmer's point of view, what we want to prove is that if I implement a function of this type, then I can map that function into a value of this type. And if I have a value of this type, then I can map that value into a function of this type. And these mappings are one-to-one in both directions. This is what it means from a programmer's point of view, that these two types are equivalent. It means that I can define functions, which I could here write in the Dhall language, from cy and to cy, from Church-Yoneda to Church-Yoneda. And these functions are parameterized by arbitrary functors f and g. And for arbitrary functors f and g, I can map from cy fg, which is this, to g of L fix f and back. So these two functions I can implement in general for any f and g, which takes just a few lines of code to implement. And here you see I'm using the f map of the functor g, and here I use fix, which is a function that is standard for the Church encoding, and it uses the f map of the functor f. So I do need both functor evidence values for f and g in order to implement these two mappings. And then, as a programmer, what I need to prove is that these two functions are inverses to each other. So if I take any value of the first type, then I can take 2cy of that, and then from cy of that, and I need to get again the value I started with. And in the other direction, if I start with a value of that type, then I take from cy of that value, and then 2cy of that result, and then I should get again the value I started with. And as a programmer, I need to prove that by substituting the code of the functions into each other and simplifying the results using the laws that I know. And this is what needs to be done, and I show how to do that in this book in all detail. In one direction, it is easy, or easier to show. You just substitute, and then because of the identity law of the functor, you get the identity function. And the second direction is more difficult because it is usual in these kind of proofs that in one direction it is easy and the other direction is difficult, because actually one type is much more complicated than the other. So if you look at these two types, this type is a higher order function with a type parameter, and the other type is just a functor applied to a fixed point. So it is a simpler type here than this. And because it's a simpler type, if you start with a simpler type, go into the complicated type and come back, it's easy to show that you get again a value of a simple type. But if you start with a complicated type, go to the simple type and come back, then you get another function with a type parameter, and you need to now show that that function is equal to the initial function. And proving the equality of two functions is harder, especially since it's a higher order function. So you need to prove that when you start with some value that is cy, which is of this higher order function, and you apply that to an arbitrary function of type fr to r, then you get the same results, because that's how you prove that two functions are equal. When you apply the two functions to an arbitrary argument, you get the same result. But that's a harder calculation to do. And actually, if you do that, you get a different function. You get this. And it's not obvious that it is equal to applying the initial function to the same arguments. It's far from obvious. And actually, you can only show that if you assume some law that the cy satisfies. The dinaturality law is not easy to formulate because it's not really just an equation. It's an equation involving two arbitrary p and q, p being this value and q being that value. So these p and q must satisfy an equation which is written like this, which is some kind of a law that they satisfy. So for any p and q that satisfy this law, some other equation must be satisfied. Now, namely, f of px must be equal to q of something. And so that is the law that p and q that is the law that cy will satisfy for arbitrary p and q that themselves satisfy another law. This is a very difficult condition to use. It's not an equation. It's an equation that only works when some parameters satisfy another equation. And that's really not an easy thing to work with. And so I try to go very slowly here. I write down this law and write out all the substitutions that you have to do. So when you do these substitutions, then the dinaturality law directly gives you the equation that you want to prove. And this is what this proof shows. I would like to also show the Church-Yoneda identity, which is a similar identity for the greatest fixed point types. And the greatest fixed point type is encoded in this way. So this k is an arbitrary functor, f is an arbitrary functor, nu f is the greatest fixed point of f, and so k of nu f is equivalent to this existential type. And if this were not k but just identity, then nu f is encoded like this without k. So that is the Church encoding of the greatest fixed point using existential types. Again, this paper by Wadler, which I will give in the links to this talk, sketches the proof of why the greatest fixed point is really encoded in that way. There are, again, quite a few steps that Wadler does not explain quite in detail, and it will be hard to follow for people not familiar with this subject. And it took me quite a while to fill in those gaps as well. So I write them all out in my book. Similarly to the Church-Yoneda identity, the Church-co-Yoneda identity adds here an arbitrary functor, and then the result is that that functor is applied to the greatest fixed point. Now this is how you would express this in Dhall. It has a bit more verbosity because the product needs to be represented as a record with names of fields. But other than that, essentially that is how you would write it in Dhall, very similar to the mathematical notation of type theory. And again, as a programmer, what you need to show is that you can have a value of this type, a value of this type, and two functions that convert between these types. So these are the two functions that I'm going to define. And then you have to show that these two functions are inverses to each other by showing that the round trip in both directions is the identity. Now, this is more complicated than for the Church-Yoneda identities because of the existential type. The existential type needs to be encoded using the church encoding. So it needs to be encoded, so we have two universal quantifiers when we encode that. So we have on both sides of this identity, both the CCOY and KG contain these universal quantifiers. So that's a more complicated proof, and it takes me more time to do this. And actually it takes more laws to be proved because of these quantifiers. Each of these quantifiers implies by parametricity some kind of naturality law. So again, we make the assumption that whenever we have a universal quantifier, then the function under it cannot examine what actual type it is getting at runtime. And so the code of that function must work in the same way for all types T, and similarly here for all types R. So we make both of these assumptions. These assumptions are true for Dhall because Dhall does not have any means of checking what type something is at runtime. And any programming language that works with type parameters, but where you restrict yourself to the code that does not examine those type parameters at runtime, will give you the same property, the naturality law, and in this case, the strong dinaturality law, and some other laws that hold due to parametricity assumptions. Naturality law for values C, and another law that I had to prove for the existential quantifier, which I will not talk about right now. So in any case, what I would like to conclude with is that we have an encoding of the least fixed points, we have the encoding of the greatest fixed points, and we have this combined identity which looks like Yoneda and Church encoding together, where you encode a functor applied to a fixed point at once. And this seems to be a very useful thing when you work in system of omega or in lambda calculus with higher rank types, because it is really very convenient that you can encode a functor applied to a fixed point in a simpler way. It's actually simpler to work with. And I use the Church-Yoneda identity mostly in proofs in this book. So for example, the so-called unrolling lemma is that if you have a recursive type, which is defined like this with two different functors, then intuitively this is f of g infinitely many times. Now, of course, this is not rigorous, but it suggests that t is f of something, which I call u here, and that u is like this. Now, it appears to be intuitively reasonable to think that. And actually, it is true. So if u is defined as the least fixed point of this, and t is fu, then actually t is the least fixed point of this. In order to prove that, I use the Yoneda identity, and this seems to be necessary. So if I say what is t is this in the church encoding, and u is this in the church encoding, and then I use the covariant Yoneda identity, and I introduce one more type parameter, and I have this, and then I can get it back, and then I have this form, which is the Church-Yoneda identity. And so the Church-Yoneda identity tells me that this is equal to f applied to the fixed point of this, which is u. So t is equal to f of u. So the Church-Yoneda identity directly allows me to prove rigorously the unrolling lemma for the types. And similarly, I do that for the greatest fixed points using the Church-Co-Yoneda identity. Another application is the church encoding for mutually recursive fixed points. So if we have this kind of mutually recursive types, then when we do the church encoding for them, we get something that's of the form of the Church-Yoneda identity again, and then we can use that. And here is something I call the nested fixed point lemma, which is another application of the Church-Yoneda identities. And it's an interesting thing, which is that if I have a bifunctor, so which is covariant with respect to both type parameters, and I take the fixed point with respect to each of them separately, so first with respect to x, the result is a functor in y, and then I take the fixed point of that functor. Then actually it's equivalent to just taking this fixed point with respect to x. And this holds both for the least fixed point and for the greatest fixed point. So I can write it like this. So if I have a fixed point, a nested fixed point with respect to x and y separately, it's the same as so-called, so to speak, a diagonal fixed point, where you just take a simple fixed point. So that allows you to simplify fixed points. And to prove that, again, I found that I can use the church encoding and then the Church-Yoneda identity, because I get, again, expressions like this. And that is quite useful to have the Church-Yoneda identity on hand. And similarly, to prove this for the greatest fixed points, I use the Church-Co-Yoneda identity. Now, and in this book, I use the Church-Yoneda and Church-Co-Yoneda identities in a few more places, in particular when working with monad transformers, such as list monad transformer or free monad transformer, because it is much easier to use that to define encodings. So let me conclude by saying that this identity is certainly not something I invented, although I don't think I've seen any place where it is proved. It is mentioned in the literature, so I found several mentions of it in the literature. One is here. I will give the link. A paper by Tarmo Ustalu, but there is no proof there. And there is another paper that also cites this, again without proof. There are a few other papers that cite this identity but do not go through the proof in detail. But the proof is quite analogous to that of the church encoding. So if you know how to prove that this type is a church encoding, that this type is the least fixed point of f, if you know the details of that proof, then it would be very easy for you to do the proof for the Church-Yoneda identity as well. And because there is never any question about this, you won't find literature that explains how to prove either of them in detail. So my book is one of the very few sources that you can use to go through the proof in every detail. This concludes my tutorial.